Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, longest common subsequence. So the gist of this is we get two strings, text1 and text2, and we want to return the longest common subsequence. And if there is no common subsequence, we want to return 0. Let's see some examples. So it's basically the common letters in order from each. So let's say take a look at the first one. So we have A here, and we have C, and we have E, C and E. So it's three letters, right? The length is 3. Here it's all of them, so the length is 3. Here no common ones, so 0, right? So that's the idea. And we are told here that we have only lowercase English letters. Okay, so let's see how we can solve this. Definitely, like if you take a look here, we can just, what are the possibilities, right? We can just do a recursive solution, right? And what would be the state that we need? We definitely know that we need the position in each of the strings, right? So we know that we need I, which would be the position in text1, and we need J, which can be the position in text2, right? So with these two, let's call it common subsequence, right? Okay. So with just these two, how do we recurse? Well, the only case where we want to add 1 to the common length, right, is if text1 at position I is equal to text2 at position J, right? Because that means there is a common letter, so we need to add 1 to our common subsequence. But then where should we go? So I and J are both equal, so we should go to the next letter, right? So let's say, for example, here we have A, B, C, D, E, and here we have A, C, E, right? So first I is here, and I is here. So we find that they are equal, right? So we want to add 1 plus go, so this is J. Advance this and advance this, because they are equal. We counted them, so we shouldn't double count them or stay for one of the indices there, right? So we want to do I plus 1 and J plus 1. Now, if they are not equal, what should we do? Well, if they are not equal, let's say maybe this was B, then what we need to do is both try moving I and seeing if we get equal, or moving G and see if we get equal, right? So in this case, moving I is the better one because we get a match. But what if it was C here, right? Yeah, what if it was C like this? Okay, then no, not that. What if it was, let's see what we can do here. Yeah, what if it was C here? Yeah, so if it was C in that place, then moving J is what makes sense. So we need to try both because we don't know in advance. So what this means is that here we need to try and advance G and try advance, and let that proceed and see what happens, right? We don't need to advance both at the same time if they are different, because we will end up advancing I, and then in a next call we'll end up advancing J, so they would be equal or anyway, right? So we'll check the two next one anyway. So we don't need to do it if they are not equal, because with this it will happen. And what we are looking for is the longest one, so we need to keep track of the max. So we just need to keep track of some max here. Can be we can initialize it to maybe minus infinity, and then so that it's as small as possible, and then just assign it as we go, right? And do the same thing for this one, get the max with this one and get the max with this one, right? So yeah, that's pretty much the idea, the gist of the idea of the recursive approach. So let's just implement it here. So what do we need to do? We said common subsequence with I and J, and we need to do this call. So if so we just need to have mx start out as minus infinity, as we said, and then we need to take the max each time. So this would be mx is equal to the max of mx in this, and similarly and this as well, right? Because we want to try both. Okay, so now that we have that, max in Python can take multiple, more than 2. We just need to return the max. And then we need to handle our base case. Our base case is when we reach the end, right? Let's say we advance this and reach at the end. We should stop because there is nothing to compare to for this one with this one. Let's say we reach at the end here, but this I may be still here, right? Because we do I plus 1 in successive calls. So in that case, also we need to check our base case. So we say if I is equal to the length of text1, and or actually, so whichever one has reached the end, we should stop and return just 0 because there is nothing left, and just let it propagate, and it will propagate and add the ones that where we encountered equal characters, right? Okay, so now we just need to call the initial function, which is from the start positions, which are 0 and 0, and just return that, right? Okay, let's see if this works. So it works for these test cases. But one thing you may notice is that there are actually multiple calls to the same thing, right? So let's say, for example, this position here, which is basically 1, 1, right? So if this was A, then we would arrive to that from this call here, but we'll also arrive to it from calling first 1, 0. So we'll call first 1, 0, right? And then we'll come here and there is this variant, okay? So that would mean it will then call 1, 1, right? So we would have a state repeating twice. And so if we don't do something to save the result of the first call, we'll do this call again and recalculate all the way to the end of the traversal of I and j, right? So that's obviously not good. So we can just use memoization here to save the result, right? So how do we do that? Well, the easiest thing is to just create a map, right? And so here we could just have our map and check if ij in our memo map. Then we just want to return that and not calculate it because we already did. So we just return. And then we want to save the result that we have so far. So that will be is equal to mx, and we can return it. Okay. And that should be it, really. So if we run this and submit, it passes, right? Okay, so now in Python you could also just, let me show you just for the sake of examples, we can use LRU cache annotation. So let's remove this. Could just use LRU cache, and that should work as well. Okay, we just need to not limit the size, or we could just use cache as well if we want. Okay, so with this recursive function, this tells us a little bit that we should be able to use dynamic programming. So let's try it. Okay, so let's see how we can do the dynamic programming solution. So first we need to come up with our DP recurrence relation. So we can actually just get inspiration from this one. So DP of I, we know that there are only 2 states, right? So either text1 I was equal to text2 j, right? So if it was equal, then we know that DP of ij, same thing, the state, since the state here was I and j, that means the state of the DP is going to be the same thing. So this is going to be equal to 1 plus here. So here we go we go forward, right? But DP, we save the previous result and use them in the next result. That's the idea. And so here we look back to see if DP of I minus, how many, what's the length of the longest common subsequence ending at I minus 1, j minus 1. So what DP of ij represents for us here is longest common subsequence between for text 1 and text 2 ending at I and j. So ending at I for text 1 and at j for text 2. So if at I and j are equal, let's again take the example here, right? So let's say, for example, in this C, we find that they are equal, I, j. Okay, so it only makes sense to look at, okay, what was the length of the longest common sequence between this one and this one, between the prefix, right? And we can just add 1 because now they are equal, right? So that's the idea of doing this here. Now, otherwise, what should we do? Otherwise, well, we have this case. So we need to do otherwise dp of ij. It's going to be the max. Again, here we want to take a look at I minus 1, but j is still at this position to see what's the common one there, because let's say this was b, then if we take a look, then we would have had 2, right? Or the other case would be same thing but reverse it. So here, so we want to, let's say here maybe, and this one is here. We want to take a look at this one compared to this one, right? So it's going to be I minus 1, j, and I, j minus 1, right? So the previous one in the first one, or the previous one in the second one, right? And then what should we return at the end? So this would be our recurrence relation. So with dynamic programming, you need to find recurrence relation. You need to define your state, right? We need to define our base cases, and we need to define our goal that we want to return. What's the goal? The goal is the length of the common subsequence in between the entire 2 strings, right? So basically I ending at the end of text 1 and j ending at the end of text 2. And so what would that be? That would be just length of text 1. Let's say n1 is the length of text 1, and n2 is the length of text 2, right? Then it's going to be of n1 minus 1, that's the last position, and of n2 minus 1, right? Okay, unless like we do our DP state. We can also do our DP state with indices starting from 1 to make it easier, because we would need to do I minus 1 here. Then in that case, it would be just like this, right? If we do indices starting from 1 for DP, okay? And now the base case. What should be our base case? Well, since we did, if we do indices starting from 1, then we can just start checking from 0, right? And so initially all of them are 0, because initially we haven't calculated any length, right? So just initialize in a DP to 0. And so with this, we should be able to write our DP solution. So let's just do that. So the first thing we need to do is write our DP for DP array. So it's going to be, so let's first do n1 is equal to the length of text 1, and n2 is equal to the length of text 2, right? And this is going to be the range of the first one, the second one, which is j, so that needs to be the length of text 2. And since we are starting in this indexing from 1, we want to add +1 here. And we need also a similar thing for n2, n1. So this is for I indices, right? Okay, so now that we have that, what do we need to do? Well, we just need to traverse and do our order of occurrences here. So we'll start indexing from 1, and we will go all the way to n1. That's for I. And for j, we'll go all the way to N2. And then we can use our recurrence relation that we had here. So this is text2. And then at the end, we can just return our goal function that we mentioned above, right? And that should be it, really. So let's run this. Yeah. We could either do it like that or do it like this, right? Okay, so it looks like in this out of range, that's because this needs to check -1, right? Because remember, for our DP, we started indexing from 1, but the string is indexed from 0, right? So that's why. Okay, so let's submit. And this passes, right? Yeah, so this is the DP solution. In terms of time complexity, it's of N1 by N2. So N1 being the length of text1 and N2 being the length of text2. And space, it's also of N1, N2. We can optimize this actually to use just one array, because you can see here, we use only the previous row and the previous column each time. So I'm not going to explain that solution, but it's just something for you to do as an exercise and to try to train a little bit more on dynamic programming. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.